Hi to everyone and welcome once more to another video in our YouTube channel. So in this video we are going to be looking at the solutions to Polytechnic Yaoundé Mathematics Paper 1 2021, and we are going to be solving the problems which was divided into three parts: part A, part B and part C. Now the three parts were independent, so the question paper itself was divided into two exercises and then these problems. So the two exercises were already solved and uploaded to the YouTube channel. So after watching this video, make sure you navigate through the YouTube channel in a playlist under further maths and you identify exercise 1 and exercise 2 solutions, and then you can also watch the solutions. So for those of you who have not subscribed to the channel, endeavor to subscribe, share the video to your friends since you're writing very soon, like the video if it is good, and make good comments about the video. Alright, so we are going to begin with problem part A, which was allocated for 4 points. It reads, in this part, assume alpha to be 2, c to be 1, and k to be equal to 1. And considering the function defined by f of x equal to 1 over x squared e raised to the power negative 1 over x, for x greater than 0 and f of 0 equal to 0. Calculate the limit as x tends to 0 from above of my function f. Alright, so the limit as x tends to 0 from above of f of x is the limit as x tends to 0 from above of 1 over x squared times e raised to the power negative 1 over x, because 1 over x squared e raised to the power negative 1 over x is my f of x. So we are going to do the analysis together. Alright, so as x tends to 0 from above, 1 over x tends to positive infinity. So it means negative 1 over x will be tending to negative infinity. So e raised to the power negative 1 over x will be tending to 0 because it's tending to e raised to the power negative infinity. So it tends to 0. Now 1 over x squared here will be tending to positive infinity as x is tending to 0 from above. So we can draw a conclusion that as x tends to 0 from above, 1 over x squared, since it's tending to 0, and then 1 over x squared is tending to positive infinity, e raised to the power negative 1 over x is tending to 0. So the product of the two will be tending to 0 because this is tending to 0 and this is tending to positive infinity, and we are doing the product, so finally it's going to be tending to 0. So the limit as x tends to 0 from above of my function is equal to 0. Alright, next, study the variation of f, the sense of variation, and the limit of f at positive infinity. So the variation is just to tell the examiner the values of x for which the function is increasing, the values of x for which the function is decreasing, and the values of x for which the function is constant. Now, to get all these values of x, we need the first derivative of the function. Alright, so the function is given by 1 over x squared e raised to the power negative 1 over x, so we need the first derivative. So we use the product rule. So for the product rule, let's begin by keeping 1 over x squared constant. So keeping the function 1 over x squared, we differentiate e raised to the power negative 1 over x. So differentiating e raised to the power negative 1 over x, we differentiate the function at, in the power, and then we multiply by e raised to the power negative 1 over x too. So at the end we get 1 over x squared times 1 over x squared e raised to the power negative 1 over x. Then plus, we now keep e raised to the power negative 1 over x constant, and we differentiate 1 over x squared. Differentiating 1 over x squared, you get negative 2 over x cubed, then times our e raised to the power negative 1 over x. Alright, so with that we can simplify. The first term here gives us 1 over x raised to the power 4 e raised to the power negative 1 over x. The second term remains. Now from the two terms, I can factor out e raised to the power negative 1 over x divided by x cubed. Removing that from the first term, I'm just going to get 1 over x, and removing that from the second term, I'm just going to be left with negative 2. Now I can look for the LCM here, and I'm going to get e raised to the power negative 1 over x cubed times 1 minus 2x all divided by x as my f prime of x. I can multiply the denominators and I get my f prime of x to be equal to this function. Now at turning point, meaning when the function is constant, the first derivative is 0. So the first derivative being 0 means that e raised to the power negative 1 over x times 1 minus 2x all divided by x raised to the power 4 is equal to 0. So I can divide both sides of the equation by this quantity here, and I multiply both sides of the equation by this quantity. Doing that, I'm just going to be left with the numerator, which is 1 minus 2x equal to 0, meaning that x is equal to half. Now we need the corresponding y coordinate, which is f of half. So f of half, we just come and replace our half with our x with half here, and we are going to get 4 e raised to the power negative 2. So we can draw a conclusion that at a point half 4 e raised to the power negative 2, the function is constant because the first derivative is 0. Alright, next, for the function to be monotonic decreasing, then the first derivative should be less than 0. So the first derivative being less than 0 means that the equivalence, because it's a first derivative, so e raised to the power negative 1 over x times 1 minus 2x, all divided by x raised to the power 4 should be less than 0. Now, we know that for something to be less than 0, I'm going to group two different functions, but before doing that, let's analyze this function together to see when it is negative and when it is positive. Now, we're being told that x is greater than 0. So since x is greater than 0, it means that what? That x raised to the power 4 is greater than 0. So the denominator is positive. Now, this factor in the numerator here is also positive because it is the exponential function. So at the end, if I take e raised to the power negative 1 over x divided by x raised to the power 4, it will also be positive. So at the end, we have this numerator here, this factor here divided by this denominator here is positive. So it means that for all of this to be negative, then just this numerator here needs to be negative, since we are multiplying out a positive number with a negative number. Alright, sorry, a positive number with a certain function, and we want our result to be negative, so it means that function must be negative because e raised to the power negative 1 over x divided by x raised to the power 4 is already positive. So for this to happen, then the numerator here needs to be negative. So for the numerator to be negative, it means we can divide all through by the negative sign. We get 2x minus 1 being greater than 0, so x is greater than half. So we draw a conclusion that the function is monotonic decreasing for x greater than half. Alright, if the function is monotonic increasing, then the first derivative is greater than 0. The first derivative being greater than 0 means that e raised to the power negative 1 over x times 1 minus 2x, all divided by x raised to the power 4 is greater than 0. We carry out same analytics. X is greater than 0 as we have been given initially. X raised to the power 4 will also be greater than 0, and the exponential function is always greater than 0. So it means that the ratio between e raised to the power negative 1 over x and x raised to the power 4 is also greater than 0. So for this function here to be greater than 0, then the numerator here must be greater than 0, since we have found out that e raised to the power negative 1 over x raised to the power 4 is already greater than 0. So we just need to solve for 1 minus 2x greater than 0. 1 minus 2x greater than 0 means that we can divide all through by the negative sign. We get 2x minus 1 less than 0, so x is less than half. But x is less than half, but we're being told that it was also greater than 0. It means that it is greater than 0 but less than half, so it is between 0 and half. So we can draw a conclusion that the function is monotonic increasing for x in the interval 0 to half, or x between 0 and half. Alright, next we are asked to calculate the limit of f as x tends to positive infinity. So the limit as x tends to positive infinity of my function, we are going to analyze together. So as x is tending to positive infinity, 1 over x is tending to 0 from above. So negative 1 over x will be tending to 0 from below. And hence, e raised to the power negative 1 over x will be tending to e raised to the power 0, which will be tending to 1, since the power is tending to 0. Now, 1 over x squared here will be tending to 0 from above, as x is tending to positive infinity. So at the end, we can conclude that the limit as x tends to positive infinity of the function is 0, because 1 over x squared is tending to 0, and e raised to the power negative 1 over x is tending to 1. So the product of the two will be tending to 0 times 1, which will be tending to 0. Now, we need to trace the variation table of the function. So I'm going to indicate the previous information that we had. First, we had that the function is constant at this point, that is at x equal to half. It is monotonic decreasing for x greater than half. It is monotonic increasing for x between 0 and half, and the limit as x tends to 0 from above was 0. Now, the variation table is a table that contains the vertical asymptotes, the turning points, and the domain of definition of the function, the intercepts as well. So first, we are going to begin with where x is being defined. X is greater than 0, meaning that it begins from 0 and ends at positive infinity. Are there vertical asymptotes? No, because the limit at 0 gives us 0, so 0 is not a vertical asymptote. Are there turning points? Yes, so we need to indicate the x coordinate of those turning points. Are they intercept? Yes. x equal to 0 is an intercept because we were being told that f of 0 is equal to 0. So I just need to indicate the x coordinate of the intercept of the turning point, which is x equal to half. Now we need to check the variations, how the function is behaving. So we need the sign of the derivative. Is it positive or is it negative in which interval? So we saw that in the interval 0 to half, in this interval the function is increasing, meaning that the derivative is positive. Now in the interval x greater than half, the function is decreasing, meaning that the derivative is negative. So with this positive and negative signs of the derivative, we can now indicate the shape of the function in the various intervals. Now since the function is the derivative is positive in the interval 0 to half, it means that the function is monotonic increasing. But where does it increase? It increases from where to where? That's the question. So it increases from the limit as x tends to 0 from above, which is 0, right up to the turning point, the y coordinate of the turning point. Since the x coordinate is half, the y coordinate is 4 e raised to the power negative 2. Now in the interval half to positive infinity, the function is decreasing. So basically it decreases from this turning point here. So this turning point is said to be a maximum turning point. So it decreases from this turning point here right up to the limit as x tends to positive infinity, and the limit we have found is 0. So this is the variation table of our function f of x. Okay, next, write the equation of the tangent t to the curve c of f in the orthogonal reference frame OIJ, 1 unit on both axes for 10 centimeters at the point x0 with x0 greater than 0. So the equation of tangent of a line at the points x0, y0, because our y0 is actually equal to f of x0, because I'm looking for the equation of the tangent, but it is supposed to be at a point, and I've given us the x coordinate of the point. The x coordinate of the point is x0, so it means the y coordinate, I'm just going to call it y0. We are going to see that to get y0, I just need to replace x0 in my function f of x. Alright, so the tangent, the line is given by y minus y0 equal to m into x minus x0. My m is simply the derivative of my function at the point x0. So previously we found the derivative of the function. So the derivative of the function at the point x0, we just replace x here with x0. You get the derivative of the function at x0. So it gives you your m, which is the gradient of the tangent line. Alright, now your y0 is simply f of x0. That's the y coordinate of the point. So f of x0 becomes, just replace, since your f of x is 1 over x squared e raised to the power negative 1 over x, you replace x with x0 and you get 1 over x0 squared e raised to the power negative 1 over x0. So you just replace the various unknowns into the tangent. I get the line to be y minus, this is y0, this is m, into x minus x0. Alright, so with that, we simplify, we multiply all through by x raised to the power 4, and we get this. So this is the equation of the tangent line at the points with at the points x0, y0, and x0 is greater than 0. Okay, next we have to determine the value of x0 given that the tangent passes through the origin of the reference frame. So the tangent passing through the origin means that the point 0, 0 belongs to my tangent. So the point 0, 0 belongs to my tangent means that when x is equal to 0, y is equal to 0. So in the place of x, I'm going to replace 0. In the place of y, I'm going to replace 0. So this is y, replace 0. This is x, I replace 0. I simplify. Here I'm just going to get 0, then minus this, I just get negative of it. Here I'm going to get 0 minus this, I'm going to get negative of it. Now the terms in red will cancel out, and then I'm going to get this. Now since x is greater than 0, it means, since x0 is greater than 0, it means that we can divide both sides of this equation by x0, but the negative signs will cancel out, and then we can divide both sides of the equation by x0 because it can never be 0. So doing that, dividing x0 on both sides, on the left hand side we are just going to be left with x0. On the right hand side, the x0 cancels and we are going to be left with 1 minus 2x0. So with that, we can add 2x0 on both sides. We get 3x0 to be equal to 1. So the x0 is equal to 1 divided by 3, and clearly it is greater than 0. Alright, we are asked to draw the curve C showing clearly the points x with x equal to 1, 2, and with x equal to half, 1 and 2, and then we should also draw the line T. So this is our function that we need to sketch, and we are supposed to show clearly a point whose x coordinates are half, 1 and 2. Alright, so this is our variation table that we had earlier, because we are going to follow the variation table to plot the graph of f of x, which is the curve C. Alright, so that's our reference frame. The vertical axis is for y. Now the horizontal axis is for x. But since the limit at positive infinity was 0, it means that the line y equal to 0 is a horizontal asymptote. So the graph will never cut that line again. Now we've been given some informations. We can look for f of 1 because we need to show the points with x coordinates half, 1 and 2. So f of 1 is equal to e raised to the power negative 1. Just replace x equal to 1 in the function f of x. Now f of 0 was being given as 0. F of 2, you just replace x equal to 2. You're going to get 1 over 2 squared e raised to the power negative 1 over 2, which is 1/4 e raised to the power negative 1 over 2. F of half is the y coordinate of the turning point, which is 4 e raised to the power negative 2. So we are going to indicate all these points and then we trace our curve. So we begin with this point. Is the point half, 4 e raised to the power negative 2 is the maximum turning point of the function. So that's the x coordinate is half, and then the y coordinate is 4 e raised to the power negative 2. Next, the x coordinate being 1, we have the point which is represented by 1, and then the y coordinate is e raised to the power negative 1. So the x coordinate is 1, the y coordinate is e raised to the power negative 1. Lastly, we have when x is equal to 2. So here is the origin 0, 0. Now when x is 2, our y was given as e raised to the power 1/4, sorry. So here it's supposed to be 2 1/4 e raised to the power negative half, not 1/4 e raised to the power negative half. So be careful with that that error. Alright, so we are now going to trace the graph. So you see that it increases from 0 right up to the turning points. It decreases from the turning points and it goes down to 0, but it never touches the line y equals 0 because it is a horizontal asymptote. So the limit at infinity is giving us 0, so it's a horizontal asymptote. Alright, next we need to draw the line T, that's a tangent line. But to draw the tangent line, we know the value of x0. Our value of x0 was half, was 1/3, sorry. So x0 is 1/3. So the corresponding y coordinate we are going to find. Remember, the tangent to the curve is at that point. So, and it also passes through the origin. Now we need to find the equation of that line. Previously we saw that it was given by this. That was a general equation. So we just replace x0. The x0 is 1/3. So here we have 1/3 to the power 4. Here 1/3 squared. 1 divided by 1/3 gives us 3. So we have e raised to the power negative 3. Same thing here, 2 times 1/3 and then x minus 1/3. Now we simplify by simplify 1 minus 2/3 gives us 1/3. So we get back this equation. Now we can multiply all through by 3 raised to the power 4. So multiplying the first term by 3 raised to the power 4, you just get y. Multiplying the second term by 3 raised to the power 4, you get 3 squared, which is 9 times e raised to the power negative 3. Multiplying here with 3 raised to the power 4, you get 3 raised to the power 3, which is 27. Then times e raised to the power negative 3. So at the end, we can expand this bracket. We get 27 e raised to the power negative 3x, then minus 9 e raised to the power negative 3. So 9 e raised to the power negative 3 and 9 e raised to the power negative 3 on both sides, they cancel. So our tangent line is y equal to 27 e raised to the power negative 3x. So we can now plot it, which passes through that point. It touches the curve at one point, so that's t, given by y equal to 27 e raised to the power negative 3. Alright, next determine the primitive f of small f, which becomes 0 at x equal to 1. So the primitive is just the integral. So first of all, capital F of x is equal to the integral of small f of x. But this is small f of x, 1 over x squared e raised to the power negative x. So we are going to use integration by substitution. If we let u to be the power here, if we differentiate negative 1 over x, we just get 1 over x squared dx. So finally, my f of x becomes the integral of e raised to the power u du, because the power here will just give me u, and then 1 over x squared dx is du. So finally we get, if you integrate, we get e raised to the power u plus k, but our u is what? Negative 1 over x. So f of x is equal to e raised to the power negative 1 of x plus k. But we have been told that what at x equal to 0, our capital F is equal to at x equal to 1, our capital F is equal to 0. So f of 1 is equal to 0, meaning that 0 is equal to e raised to the power negative 1 divided by 1, replacing x with 1, then plus k. So it means our value of k, which is the constant of integration, is e raised to the power negative 1. So finally we get our primitive f of x, which annuls at x equal to 1 to be e raised to the power negative 1 over x plus e raised to the power negative 1. Alright, so we are going to move to problem part B, which is radiation of a star. It was allocated for 4.5 points. Alright, so we continue with the next part of the equation. In this part, assume alpha to be 5. The intensity lambda of I of the radiation of the star for the length lambda, where lambda is greater than 0, is given by f of lambda equal to 1 over lambda to the power 5 e raised to the power negative q over lambda times e raised to the power negative q over lambda. Lambda is greater than 0. Okay, first part, show that the intensity I of lambda of the radiation of the star is maximum for a value of lambda noted as lambda 0, which is to be determined, and then show that lambda 0 is equal to k divided by 5. Alright, so when you hear maximum, we need to look for the first derivative. We equate to 0, we find the turning point, and then we show that that turning point is maximum, is that x coordinate of that lambda coordinate of the turning point yields the maximum point. Okay, so to do the first derivative, we use our product rule. We keep 1 over lambda to the power 5, and we differentiate e raised to the power negative q over lambda. We get this, plus we now keep e raised to the power negative q over lambda, and we differentiate 1 over lambda to the power 5. We get this. Now we can factor out e raised to the power negative q over lambda from both terms. Factoring it out in the first term, we are just going to be left with 1 over k over lambda, because the denominator is lambda to the power 7, so we are removing lambda to the power 6. Factoring out from the second term, we just get negative 5. So we can look for the LCM of k divided by lambda minus 5. We get this, we multiply the denominators, and we get our first derivative of f with respect to lambda to be e raised to the power negative k over lambda divided by lambda to the power 7 times k minus 5 lambda. Okay, so we know that at turning points the derivative is equal to 0. So derivative being equal to 0 means that e to the negative k over lambda times lambda to the 7 into k minus 5 lambda is 0. So k minus 5 lambda is 0, so lambda is equal to k divided by 5. Now this lambda equal to k divided by 5, we can't conclude that it yields the maximum. We can't conclude that for lambda equal to k divided by 5 the function is maximum. We need to verify, and then we conclude by showing this. So that's the value of lambda for which the function has a turning point. So we need now to verify if this turning point is maximum or it is minimum. So you can either use the second derivative test by looking for the second derivative of the function. If it is less than 0, then the function is always maximum. If it's greater than 0, then the function is always minimum. But I'm not going to use that. Look at how we are going to analyze the function. So we are going to look for the regions where the function is decreasing, the regions where the function is increasing, and then we draw the variation table and we conclude if that point is maximum or minimum. Alright, so the function is monotonic decreasing if f prime of lambda is less than 0. So f prime of lambda less than 0 means that e to the negative q over lambda to the 7 times k minus 5 lambda is less than 0. Now since the this e to the negative q over lambda divided by lambda to the 7 is always positive, because the exponential is the numerator is positive, lambda is greater than 0, so lambda to the power 7 will also be greater than 0, positive. So the ratio between two positive numbers is positive. So if we want to yield a negative result by multiplying this positive function here with another function, then this function here must be negative. So solving this inequality is equivalent to solving k minus 5 lambda less than 0. So k minus 5 lambda less than 0 means that we can divide all through by the negative sign. We get 5 lambda minus k greater than 0. So it means our lambda is greater than k divided by 5. Alright, If the function is monotonic increasing, then the first derivative is positive. First derivative being positive means that e to the negative k over lambda times k minus 5 lambda all divided by lambda to the 7 is positive. Now since this term here is already positive, then for this product to be positive, then our k minus 5 lambda should automatically be positive. So we can divide also by the negative sign and we get 5 lambda minus k less than 0. So it means lambda is less than k divided by 5. So since we know that lambda is greater than 0 and here lambda is less than k divided by 5, then it means that the function is monotonic increasing for lambda being between 0 and 5. Now this is a variation table. It's almost similar to what we had earlier. Now the limit at 0 is 0. As lambda tends to 0, my f of lambda will also be tending to 0. As lambda tends to positive infinity, my f of lambda will be tending to 0. Now the lambda coordinate of the turning point is k divided by 5. Now the y coordinate of that turning point is f of k divided by 5. Now the function is monotonic in the interval 0 to k divided by 5, that is for lambda. The sign of f prime of lambda is positive because in this interval lambda in the interval 0 to k divided by 5, our f prime of lambda is greater than 0, so the function is monotonic increasing. So it increases from 0 right up to the y coordinate of the turning points, and then in the interval lambda greater than k divided by 5, the first derivative is negative, so the function is monotonic decreasing. So it decreases from the y coordinate of the turning point right up to the limit at positive infinity, which is 0. So we clearly see that this is maximum because it increases to a certain point and then decreases. So this guy here is maximum. So we can conclude that our lambda 0 is equal to k divided by 5 because it is the lambda coordinate of the turning points. And since we have seen that the turning point here has a maximum value, then for lambda 0 equal to k divided by 5, the intensity of radiation is always maximum. Alright, so the next part of the equation reads: the intensity radiation of the star for length lambda belonging to the interval lambda 1 to lambda 2 is given by arrow of lambda 1 lambda 2 to be the integral from lambda 1 to lambda 2 of I of lambda d lambda. Now first, determine the primitive I of lambda in the form capital F of lambda equal to A divided by lambda q plus B divided by lambda square plus C over lambda plus D times e raised to the power negative q over lambda. A, B, C and Z are real numbers to be determined. Alright, so our capital F of lambda is the integral of I of lambda d lambda, which is the integral of 1 over lambda to the power 5 e raised to the power negative q over lambda d lambda. Alright, so we are going to use integration by parts. So we begin by letting u to be 1 over lambda to the power 5. Where we differentiate, we get negative 5 over lambda to the power 6. Now our dv will be e raised to the power negative k over lambda d lambda. Our v, we just integrate, we get lambda squared over k e raised to the power negative k over lambda. So according to the formula, we get uv minus the integral of v du. Doing it, you get your f of lambda to be equal to this. So we can simplify to get our f of lambda to be e raised to the power negative k over lambda divided by k lambda q plus 5 over k times h of lambda. H of lambda is this integral in red. Now we are also going to integrate h of lambda using integration by parts. So we let u to be 1 over lambda to the power 4. So we are on this integral now. 1 over lambda to the power 4 to be u. We differentiate, we get negative 4 over lambda to the power 5. Now our dv is e to the negative k over lambda d lambda. Our v, we integrate, we still get the same response. So our h of lambda is uv minus the integral of v du. So when we simplify, we get this response. The integral in red is p of lambda. So we can further get our f of lambda by replacing the h of lambda with its equivalent, which is this. So it means my f of lambda is all of this, because I have the first term here plus 5 over k times h of lambda. This is h of lambda. I multiply all through, I get all of this. Remember, my p of lambda is the integral in red. I'm still going to use integration by parts to get it. So we get here is supposed to be divided by k squared p of lambda, not divided by k. We multiply 5 over k with the first term here, we get 5 over k squared. Multiply with the second term here, we get 20 over k squared p of lambda. Alright, so that's our f of lambda. Okay, so we are now going to integrate p of lambda with using integration by parts again. P of lambda is the integral in red here. So we do the same thing. We just let u to be 1 over lambda to the power 3. We differentiate, we get negative 3 on lambda to the power 4. Our dv is e to the negative k over lambda d lambda. Our v is the same response. So our p of lambda is uv minus the integral of v du. So you just replace the various missing terms, and we get our p of lambda to be e to the negative k over lambda divided by k lambda plus 3 on k times t of lambda. Our t of lambda is simply the integral in red. So we are now going to look for f of lambda in terms of t of lambda. So I just come and replace p of lambda with its equivalence, and I get this. So I multiply 20 times this guy here, I'm going to get this. Then 20 times 20 on k squared times 3 on k, I'm going to get 60 on k cubed t of lambda. Now this is my f of lambda. Now we need to integrate t of lambda, so we are going to use integration by substitution. So we are just going to let u to be negative k over lambda. When we differentiate, we get our 1 over lambda squared d lambda to be du divided by k. Alright, so with that, we just replace, we get our t of lambda to be 1 over k e raised to the power u du, e raised to the power u du, not d lambda. So you just get 1 over k, integrating e raised to the power u du, you just get e raised to the power u. But what is u? Your u is negative k divided by lambda. It means your t of lambda is equal to 1 over k e raised to the power negative k divided by lambda. So from there we can replace back the t of lambda to get f of lambda. So we just replace 1 over k e raised to the power negative 1 over negative k over lambda to get my f of lambda. So I can simplify, I get all of this, and then I factor out e raised to the power negative k over lambda. So I'm going to get my f of lambda to be this. So if I compare with this, I can get the coefficients. A is going to give me 1 over k because it is a coefficient of 1 over lambda cube, or the numerator the coefficient of 1 over lambda cube is 1 over k. The coefficient of 1 over lambda squared is b, which is 5 over k squared. The coefficient of c of 1 over lambda is c, which is 20 over k cube, and the coefficient of the constant is d, which is 60 divided by k raised to the power 4. So the process, what you're doing here, you're just doing numerous integration by parts and reducing the function into a function you can easily integrate without using integration by parts. Okay, so next we have to calculate the limit as lambda tends to infinity of f of lambda and the limit as lambda tends to infinity of f of 1 divided by lambda. So this is our f of lambda that was being given to us. So the limit as x tends to infinity of f of lambda is the limit as x tends to infinity of everything here, because this is f of lambda. So clearly we see that as lambda tends to in positive infinity, the numerator here will be tending to 0, because lambda is tending to positive infinity. K over lambda will be tending to 0. There's nothing like negative 0. So e raised to the power, the numerator will be tending to e raised to the power 0. Now here, since lambda is tending to positive infinity, this will be tending to 0, this will tend to 0, this will tend to 0, and here we just have the constant. So 0 plus 0 plus 0 is 0, then plus the constant, then times e raised to the power 0. E raised to the power 0 is tending to 1, so at the end we get the limit as lambda tends to infinity of f of lambda to be 60 divided by k raised to the power 4. Now our f of 1 over lambda, we just replace lambda with 1 over lambda. The first term here, since in the denominator 1 over lambda in the denominator here becomes 1 over k divided by lambda cube, so it reverses. Same thing for the other terms, and same thing in the numerator here, same thing in the power here. Negative k divided by 1 over lambda is negative k lambda. So the limit as lambda tends to infinity of f of 1 over lambda is the limit as lambda tends to infinity of this junk, because it is our f of 1 over lambda. Now as lambda tends to infinity, the interior here tends to infinity, because you have this is tends to infinity, this tends to infinity, this tends to infinity, this tends to a real number, so all of it tends to infinity, the interior. Now e raised to the power negative k over lambda will be tending to 0, yes, as lambda is tending to infinity. So e raised to the power negative 1 over negative k lambda will be tending to 0. So at the end we get something tending to infinity times something tending to 0, automatically it tends to 0. So that's the limit as lambda tends to infinity of f of 1 over lambda. Okay, calculate for lambda 1 greater than 1, arrow of 1 over lambda, arrow of 1 over lambda 1 by using f. Show that the limit as lambda 1 tends to positive infinity of arrow of 1 over lambda 1 is equal to 60 divided by k raised to the power 4. Okay, so we were being given that arrow is an integral, which is the integral of I of lambda. So our arrow of 1 over lambda 1 lambda 1 is just the integral from 1 over lambda 1 to lambda 1 of I of lambda d lambda. But integrating I of lambda alone, we just get f of lambda. So since we now have limits of integration, it means that this arrow of 1 over lambda 1 is just f of lambda from 1 over lambda 1 to lambda 1. So it means put the upper limit, we get f of lambda 1, put the lower limit, we get f of 1 over lambda 1. So it means our arrow of 1 over lambda 1 is f of lambda 1 minus 1 over f of 1 over lambda 1. But we know our f of lambda 1. Our f of lambda 1, since we know our f of lambda, we just replace lambda with lambda 1 and we get this. Now what about f of 1 over lambda 1? This is 1 over lambda, so we just replace lambda with lambda 1, we get this. So this is arrow and it is precise for lambda 1 greater than 1. Next, we have to show that this limit is 60 on k raised to the power 4. So the limit of this is simply equal to the limit of f of lambda 1 minus f of 1 over lambda 1, because this is equal to f of lambda 1 minus f of 1 divided by lambda 1. So we can separate the limits. We get the limit we are looking for to be limit of f of lambda 1 minus the limit of f of 1 over lambda 1. But clearly, the limit of f of lambda 1 as lambda tends to positive infinity is the same as the limit of f of lambda as lambda tends to positive infinity, which is 60 on 4. So I replace. Now the limit as lambda 1 tends to positive infinity of f of 1 over lambda is the same as this limit, which is 0. I replace. So I do the difference and I get the limit as lambda 1 tends to positive infinity of arrow of 1 over lambda 1 to be 60 divided by k raised to the power 4 as required. Alright, so the last part C, group of stars, it is allocated for 2.5 points. Alright, so we are going to complete the equation, which it reads: the quantity of impurities present in the depth of the set z greater than 0 of the crystal of silicium is expressed in terms of t greater than 0 by n of t equal to 1 over the square root of t e raised to the power negative 2d squared on t. Show that n of t present is maximum when t of d is equal to 4d squared, and calculate the value of this maximum and note it as capital N of d. Alright, so our n of t is given by 1 over the square root of t e raised to the power negative 2d squared divided by t. So for convenience sake, since we are going to differentiate because we have seen the word maximum, we need the derivative. So with that, we write 1 over the square root of t as t raised to the power negative half. So it means our n of t is equal to t raised to the power negative half e raised to the power negative 2d squared divided by t. Now we launch the derivative. So our n prime of t, we differentiate, we use the product rule, we keep the first, we differentiate, we keep e raised to the power negative 2d squared on t, we differentiate t to the negative half. We now keep t to the negative half and we differentiate e raised to the power negative 2d squared on t. Now we simplify and then we get our first derivative to be all of this. Now at the turning points, our n prime of t is equal to 0. So n prime of t equal to 0 means that this is equal to 0. So that equal to 0, we divide both sides of the equation by this term here. We are just going to get negative half plus 2d squared on t equal to 0. So with that, we can add this on both sides of the equation. We get 2d squared on t to be equal to half. It means t is equal to 4d squared. Since it's a function of d, we can call it t of d by when we cross multiply. T goes this way and then 2 multiplies with 2d squared to get 4d squared. Now we need to show that at t of z equal to 4d squared, this n of t is actually maximum. So it is equivalent. It is we even previously showed this when we're talking about lambda, so we are going to use the same thing. So we studied the variations, so we are now going to show that at t of z equal to 4d squared, n of t is maximum. right? Because t of z equal to 4d squared is a t coordinate of the turning point, so we need to determine if the turning point is maximum or is minimum. You can either use a second derivative test or you do what I'm about to do. So if the function is monotonic increasing, then n prime of t is greater than 0. So n prime of t greater than 0 means that all of this is greater than 0. But this term here, this function here, is always greater than 0 for all values of t that is greater than 0. So at the end, for this to be greater than 0, then just this needs to be greater than 0. So at the end we get t minus 4d squared less than 0, so our t is less than 4d squared. Next, if the function n is monotonic decreasing, then the first derivative is less than 0, not greater than 0. So if the function is monotonic decreasing, then the first derivative, that is n prime of t, should be less than 0. Alright, so n prime of t less than 0 means that our n prime of t is 1 over t root t e to the negative 2d squared on t times all of this less than 0. So with that, we get all of this less than 0. It's divided through by the negative sign, we get t minus 4d squared greater than 0. So finally we get t greater than 4d squared. So we can conclude that when t is less than 4d squared, the function is monotonic increasing. So it means it increases right up to 4 when t is equal to 4d squared. Now when t is greater than 4d squared, the function is monotonic decreasing. So when it arrives that value there, it now decreases. So it means that at t equal to 4d squared, the function has a maximum turning point, which is what we are required to prove. So we are now going to find that point. So n of d is just equal to n of t of d. So I just come to my n of t, I replace t with 4d squared. I simplify and I get my n of d to be 1 over 2d e raised to the power negative 1 divided by 2. So that was all about the problems. We have succeeded to solve problem part A, problem part B, and problem part C. Like I said, the exercises, exercise 1 and exercise 2, the questions were already solved and uploaded to the channel, so do well to watch the videos. Like the video if the video is good, comment, share the video to your friends who are preparing for the concours as you. Invite them to subscribe to the channel if you have not done so yet. So see you in the next video, probably 2020 paper 1 or Polytechnic Douala 2021 paper 1.